All right, good afternoon, everyone. Welcome again to Warsaw University Astronomical Observatory Tuesday Seminar Series. And today we have a guest, a real person again. It's great to have real people visiting us. Pierre Fleury from Paris, Saclay, and IAP HD, right? The physical PhD. Yes. So actually, I have to correct it on the advert. So Pierre is from France. He did his studies in France and then moved to he did a couple of postdocs in Geneva. It was Paris, and it was
Paris was PhD.
Paris was a PhD.
First postdoc was in Cape Town.
Cape Town, yes, Cape Town,
second one in Geneva, yes, you're on track.
And then Madrid,
yes.
And now he's back on a tenure in Paris. So Pierre is working on lensing, but from a theoretical point of view, with some very interesting observational applications. So we're happy to host Pierre here. Pierre is actually staying for us until Thursday. If you're interested in talking to him more, please do so. We're actually going for dinner tonight as well. But I will not delay any further this interesting talk. Pierre, the floor is yours.
Thank you very much, Łukasz, and thank you for coming in 3 dimensions in real life. It's always a pleasure to give, again, talks in front of people and have feedback from the audience. So yes, what I'm going to talk about today is gravitational lensing. Yes, so the weak, the strong, and the line of sight. So this is a work that I've been doing for a good couple of years, maybe 3 years now. And it all started with Julien Larena and Jean-Philippe Dupuzan, who are collaborators for a long time. And Nathalie Hogg, who is a postdoc working with me at the IPHT, has joined the team recently. I hope that you, well, or maybe you recognized what I tried to imitate with this first slide, which is, oh no, has ruined my effect. Yes, that was what I tried to imitate with this. So yes, the topic, as I said, is gravitational lensing, and I think one person that talks very well about it is my friend Blondie, who puts it that way. So I think that we want to do an impression of Blondie. You have to close your eyes like this, and you need maybe a cigar or something to. But yeah, so you see this world. There's 2 kinds of lenses, my friend. Those producing multiple images and those that don't. And you don't, obviously, because you're not compact. So what Blondie is trying to say here is that we usually divide, or we distinguish between 2 very different regimes of gravitational lensing, which are the strong lensing on the one hand and weak lensing on the other hand. So they are different from theoretical point of views, from the observational point of view, and from their use point of view. So from the point of view of how we can use them, in particular in cosmology. I'm focusing here on cosmology because I'm a cosmologist, so this is what I tend to be interested in. But so yes, the first difference from a bit of an observational point of view between strong lensing and weak lensing is that strong lensing is producing multiple images, while weak lensing doesn't. Strong lensing produces very important distortions of light sources that you can actually see by eye, while weak lensing is preserving the integrity of light sources in a way that is impossible actually to notice by eye. Also, from the point of view of phenomenology, strong lensing is usually due to a most of the time, single isolated mass lump that is on the line of sight between the observer and the source, while weak lensing is usually due to the accumulated effect of many matter over densities that are all progressively accumulating on the line of sight. And finally, yes, as I said, from the cosmology point of view, strong lensing is something that we use via, for example, strong lensing time delays to measure the expansion rate of the universe, h0, while weak lensing is used for a completely different purpose, and it's used mostly to constrain the density of the universe, omega m, and the normalization or the amplitude of the fluctuations of its density that is usually encoded in this parameter sigma 8. So none of them is good or bad in itself. When it gets ugly is when you start mixing them together. So this is what we call, what I would refer to as line of sight effects in strong gravitational lensing. It's when you have weak lensing effect on the top of strong lensing, which when you think about it should always be the case, especially when we are talking about strong lensing. Oh yes, I forgot, because in this audience there are presumably many people working on micro lensing, which is just, as you know, a special case of strong lensing, but which happens usually, usually people doing micro lensing are investigating micro lensing that's happening within our galaxy. And in that situation, of course, these line of sight effects, you don't really have to care about them because they're extremely weak. But when we are talking about strong lensing happening on extragalactic scales, there are many things that can happen on the way from the source to the observer, from the source to the lens, sorry, from the lens to the observer. So this is in this context that these line of sight effects will be important, not in galactic microlensing. So yes, these effects are actually, so they are well known to be contaminants for, for these measurements of H0 using time delay cosmography, so using strong lensing time delays. Is there any issue with the, no, Mike, no, everything's fine?
No,
good.
fine. Yeah.
So yes, for example, the fact that you could have perturbations and overdensities of matter on the way at the level of the main lens, or between the source and the lens and the observer, is something that is contaminating the measurements of H0 using time delay cosmography. So it's usually being seen as a problem, as a source of further uncertainties. But these line of sight effects, or the weak lensing of strong lensing, could also be a new opportunity to do weak lensing, and this is what I'm going to talk about in this talk. So the motivation for this, or the intuition that is behind this, is the following. Weak lensing, and its main observable, that's called cosmic shear, is a particularly difficult measurement to do. And the reason for this is that, oh, I'm sorry, it's not like you can see very well. That's supposed to be galaxies over there. Okay, so is it?
Maybe we can dim the lights a little bit.
That should be fine, I suppose. Because if you switch off the lights, everyone's going to see. It's dark outside. I think it's fine. I hope I can make my point anyway. Ah, well. Don't sleep. Stop that. Not a good idea. Thank you very much. Okay, we'll see how it goes. Yes, so the idea of the measurement of cosmic shear, which is the main observable for weak lensing, is that if you have overdensities of, let's say, dark matter that are on the way between the observer and the sources, here galaxies, the shape, the apparent shape of galaxies tends to align tangentially to the overdensity of matter. So the idea is that by measuring the amplitude of this apparent alignment, you can get information about the density, the mean density of the universe, and about the amplitude of its fluctuations. The more alignment you have, the more fluctuations of density you have. But of course, this drawing that I made here is terribly exaggerated, because what you actually see is something like that. Weak lensing is weak. The effect that we're talking about is on the order of a few percent maximum. So you have a few percent distortion of things that are already elliptical and that have random orientation. So the only way to get any signal from this is to have a huge amount of statistics and observe a huge amount of galaxies and try to correlate their apparent shapes on large scales. So you need a lot of statistics to try to beat this, what we call this shape noise, the fact that you have an intrinsic shape of those galaxies that you don't control. Another problem coming with weak lensing is that sometimes galaxies are aligned intrinsically without the effect of having gravitational lensing on the way. This is called intrinsic alignment, and that can be due to just structure formation or the interaction between galaxies spins and the gravitational fields created by the large-scale structure, which is a source of contamination that you want to eliminate. And so these two things are making weak lensing an extremely difficult task. So how could we avoid this in an ideal world? As I said, the problem is that we are trying to measure very small distortions, so it's very small shear that we call gamma in general, on order of maybe 1%, that is slightly changing the shape of the galaxy in a way that's preserving its identity. Like there is no way when you see a galaxy like that to say that it has been distorted or not. There is no way to measure this shear just from observing the galaxy itself. To do that, we would need something that we would call a standard shape, just like we have standard candles to try to measure distances. So objects, the shape, the morphology of which we would control so that we could measure directly the effect of gravitational lensing. And in a sense, what I'm going to try to convince you about is that something like this could be strong lensing Einstein rings. So I proposed that we could do weak lensing with Einstein rings. So the weak lensing of strong lensing, these line of sight effects I was talking about. Important, it's not my idea, right? The first people who proposed that were just a few years ago. So Simon Wierer, and Alexandre Frégier, when they were still all at ETH in Zurich. So they proposed that idea, but what we did with my group is that we tried to push it a little bit further and make the theory a little bit more elaborate about it. So, do you have questions on these motivations before I go to the theory? No? All clear so far, I hope.
Well, you don't get Einstein radii very often. There is only one or two known.
Wait for the end.
Okay.
No, okay, the spoiler is Euclid is going to observe about 10 to the 5 lenses, strong lenses. Not all of them will be beautiful rings like this, but maybe 1 out of 10. Still 10 to the 4, right? So yes, there is, of course, another part of the motivation is that we are expecting to see many more of those things in the future. Yes. Okay, so theory. How do we model these line of sight effects? How do we model the weak lensing of strong lensing? So to do that, I'm going back to the strong lensing 101, the lens equation. So let's start from the basics. So I'm considering the situation where I have here a point source that we would observe without any perturbation. We're seeing it as light, we're propagating as a straight line in a direction beta, the source position. Now, on the way, I have an overdensity of matter, an isolated clump, like an elliptical galaxy, for example. So what we usually do is that because the scales that are associated to the lens are much smaller than the typical distances that separate the observer, the lens, and the lens to the source, we usually project this overdensity onto a plane that we call the deflector's plane. And then what happens to light when it propagates from the source to the observer and from the source to the observer is that it goes through this deflector's plane. It gets deflected by an angle that I call alpha hat. Alpha hat that is, of course, related to the physical position that I call x here, where light is reaching the deflector's plane. Now, it depends, this alpha hat depends on the density profile. So here, sigma is the projected density of this lens when it's projected along the line of sight. And so, yes, it's just 2D Newtonian gravitation that we're talking about here. But eventually what happens indeed is that we have a deflection that implies that we receive light in a direction theta, the image position, that differs from the source position. Now, the difference between the image position and the source position, so the difference between these two angles, is called I call it the displacement angle. So I try to give it a different name because there is a little bit, I think, of a confusion in the literature. I know it's like for experts, it's not really a problem, but we tend to call that this deflection angle. It's not the deflection, displacement, whatever. What happens is that, yes, this displacement angle, so the difference between theta and beta, is proportional to the deflection angle for just geometrical reasons, and features the distance between the deflector and the source, and the distance between the observer and the source. So when you write down just the fact that alpha is the difference between theta and beta, what you get is what we call the lens equation, very well-known fundamental equation of gravitational lensing, which is the equation that you want to solve for theta if you want to know the various images that a certain point source has. It's also the equation that allows you to trace back the light from a certain image to a potential source. It gives you directly beta from theta. Now, this was assuming that light propagates in straight line from the source to the deflector and from the deflector to the observer. Now, what happens if you add perturbations to this? Well, the picture slightly changes in the way that you have wiggles happening here, wiggles happening there, and the lens equation gets changed into that one that I wrote in the bottom left corner. Compared to the previous version, we added 3 new parameters that I called AOS, ADS, AOD, that are 2 times 2 matrices, and that translates how light is propagating between the observer and the source, the deflector and the source, or the observer and the deflector. Just to give you a flavor of how this works and why these terms are here in the equation. For example, this one, this AOD term. So this AOD, so we call that a distortion matrix or an amplification matrix. It tells you that because light is not propagating in a straight line, when it starts from a direction theta here, it's going to be deflected and reach the deflector's plane at a position which is not the same as if light had propagated in a straight line. And that's why this term here is involved in the argument of the displacement angle, because it changes how light is affected or how light reaches the deflector's plane and therefore how it is deflected there. So this term here is a post-Born correction that happens due to the foreground perturbations. This one, the ADS here, is due to the fact that if you have a certain deflection angle here, if you were extrapolating in straight lines, you would get a certain separation between the image and the source. And this separation is changed in the presence of background perturbations. So that's why this one multiplies the displacement angle that is related to the deflection angle. Again, don't focus too much on the details. If I had to just make a derivation of that, I would do it on the blackboard. I'm just trying to give you a flavor of how it works. And finally, yes, this term AOS that takes into account all the perturbations all the way from the observer to the source. This one is due to the fact that when you have a certain difference theta between, yes, so when you would extrapolate this position all the way to the source plane, you get something different given all the perturbations. This guy, by the way, the AOS, is the standard, it contains the standard weak lensing perturbations, in the sense that when you have a certain source like a galaxy in the plane S, the distortions that will be applied to it from the point of view of the observer are exactly these AOS. And actually, you can see that if you didn't have the main net, in other words, if alpha here were 0, you would still have a correction coming from this one. So this is a nice equation that really contains all the effects, weak lensing and strong lensing at the same time and mixing them together. Yes, what I wanted to say more about this is that we usually decompose those distortion matrices into a trace part and a trace-free part. The trace part being called the convergence, kappa, and typically this will be due to if you had, for example, roughly homogeneous matter distribution somewhere on the line of sight, this would produce convergence. It's an isotropic focusing of light, and this is why it enters into the trace of this distortion matrix. On the example that I gave here, this would contribute to the OD term and to the OS term. And the shear, on the other hand, gamma, is something that produces mostly area preserving distortions. So really it's a shear, it's a distortion, something made transforming a small circle into a small ellipse. Well, yes, it's the effect that shear produces, right? And this is due to, contrary to the previous case, is due to the presence of some mass lump that would be far away from the line of sight and whose gravitational tidal field would produce this effect. In this example here, this guy would contribute to ADS and to AOS. Okay, so here I'm doing a pause again. Is that roughly clear, or do you have questions? Is there anything that pulls your attention? Anyway, the details here are not that important. What I want you to remember is that when you do the weak lensing of strong lensing, you don't have only one shear, for example. You have three of them. You have three parameters characterizing what's happening in the foreground, what's happening in the background, what's happening in all the way from the observer to the source. Right. So I talked about both. Yes.
So the last one is not the sum of the previous.
It's a very good question. So yes, in the way I presented it, it looks like, yes, it could be the sum of them. It's not. The reason is that what they actually represent, if we think about the shear, for example, it would work for the convergence. So what OD represents here, for example, is the distortion of an object, of a light source that would be in the deflector's plane as observed from the observer's plane. So the OS term is the distortions happening for something from something in the source plane as observed from the observer's plane, and this DS1 is some distortion, something that is in the source plane but as observed from the observer's plane. And the fact that you have a change of point of view, the presence of saying like as seen from the deflector's plane, is bringing many changes to that. And for example, it changes the weight, the relative weight of a certain perturbation along the line of sight. The most efficient way to produce a DS correction is to have something that is midway between the deflector and the source. And the most efficient way to have something that contributes to OD is to have something midway between the observer and the deflector. So that's not exactly the sum. The weight of DS goes like this, the weight of OD goes like this, and the weight of OS goes like this. So you have a bit of a mix between these things, and they are independent parameters. Okay, so I talked about both convergence and shear, but in the rest of the talk, I'm going to focus on shear, because convergence is not something that you could ever observe in this context. The reason is the following. I'm going to go quickly on this, but suppose that you have only convergence corrections. So here I'm just rewriting the lens equation, but I'm replacing the matrices by just a pure convergence term. So it's just numbers that are multiplying the various quantities that I have in the equation. Well, here I can divide everything by this 1 minus gamma OS. I get this equation. And now what you can realize is that if I'm calling this beta prime, not the source, and if I'm calling this alpha prime of theta, I have exactly the same equation as if I had a slightly displaced source, which I never know where it is anyway. So the system is equivalent. And same thing here, going from this to this term is just rescaling the mass density that you would have in your lens, in your main lens. And this term is just making your lens a little bit bigger, a little bit smaller. So by just playing with the position of the source and playing with the density and the size of your lens, you can absorb completely these convergence terms, meaning that there is no way observationally to distinguish between this and this. So convergence, except if you have other non-lensing observables, is not something that you can observe in this context. So that's why I'm going to focus on shear from now on. And also I'm going to forget about the convergence, assuming that it's already absorbed by such transformation. Okay. So then comes the question. I said I want to do weak lensing with strong lensing. So can we observe from strong lensing images, can we observe those three shears? Okay, so let's try with an example. Suppose that I generate some realistic HST-like mock image. So with this, I use this strong lensing code called lenstronomy that's been written by Simon Beder a few years ago. So it's an open source strong lensing code that allows you to produce images, to fit them. It's a very nice tool that's on the market. So what I'm doing is that I'm producing this image. So here I assume that the main lens is an elliptical power law, that the source is a Cerseic profile, very standard things just to try and make an example. And then from this image, I suppose that this is an observation, and I try to fit it with the exact same model that I used to produce it, including those three line of sight shears that are entering into the game. The question is, am I able to measure them by running the big MCMC on that? So can I measure these gamma OD, gamma OS, gamma Ds? So here is the example, the result of the posterior distributions obtained from this MCMC. I focused here on only so yes, shear is a complex number, right? It has two components, gamma 1, gamma 2 is a complex number because it has an amplitude, it has a direction. So here I focused only to make things simpler on the component number 1 of the shears. We have the gamma 1 OD, gamma 1 OS, and gamma 1 DS. And so what you can see here is that it doesn't work in the sense that so yes, we do recover something that is consistent with the input. So the input is the dashed line. But when you look at the error bars here, I have here something that is largely compatible with 0 and that has an uncertainty that is larger than a few %, which is exactly the size of the signal that you would expect. So that means that trying to recover those three parameters directly is something that seems to be a bit of a dream that will not be accessible. But then you could wonder why. Why is it that we can't recover them? And you must have noticed on that plot that beautiful, very, very large ellipse that is the sign of a strong degeneracy between two parameters. Actually, it's yes, it should be a degeneracy between all three of them. The fact that the model is a bit simple is reducing that degeneracy. But here we still have this huge degeneracy between the OS and the TS term. And that's the reason of such a wide posterior. Why do we have such a degeneracy? Well, let's come back to our favorite equation. So this is the lens equation. Let's try to understand why there is a degeneracy. In the discussion I gave about the convergence, I mentioned the fact that the source is something that is unknown, and we can play with it. We can make transformations to it, and this tends to encode a lot of degeneracies. To come back, to give some detail. Oh, yes, sorry, one step here. So I'm taking this equation. I'm going to replace alpha here, the displacement angle, by its expression in terms of what we call the lensing potential, the Fermat potential. So yes, this guy is always the gradient of some potential. So I'm writing it exactly as the gradient of this quantity. Okay. For psi, it's just a definition here. So within this equation, the only observation that we can have is the position of images, the position of the pixels that are populated with light here. All the rest, meaning the three line of sight corrections, but also the potential of the lens and the position of the sources, is something that is completely unknown. They are models, they are parameters that you try to fit with model. So that means that I could play with this guy, make any transformation of it, and get an equivalent description of reality. So let's do it. Suppose that I multiply this equation with this matrix here. I do this because this allows me to kill this one here and replace it with this one. And you see where I'm coming here, because if I'm replacing this matrix by the same that is in this, I get a total derivative. That is this one. So I have the total derivative of an effective potential, which is modified by the foreground term. And I get now only one correction here, that is the multiplication of these three matrices. Why is that interesting? It's interesting because here now I have a lens equation that is the same as having one single lens modified by this foreground perturbation and a single external perturbation encoded in this matrix, a single shear in this case. I call this the minimal lens model, and this is what I'm going to use in the following. So the consequence of the presence of this term is that the shear that you would be expected to be measurable is this particular combination of the three previous ones. And this is exactly what we have seen before. We had seen that there was a very strong degeneracy between OS term and the DS term. Well, it's because they appear. There is no way to measure them independently. What you have to constrain is this guy. So yes, this explains why there was this degeneracy seen before. Now, let's play the same game again. I'm taking the same image, and instead now of trying to fit it with the full line of sight model with these three shears, I'm trying to fit it with the minimal one with only one shear at the IAP. And now, well, it works much better. So now what we have is still something that is consistent, so posterior that is consistent with the input value, but now with error bars that are much weaker. We're talking about a factor 100 here of gain in the posterior and the precision of the measurements. So, good. Questions about this, or is that clear? Or is it going too slowly? I can see some of you starting to sleep. I'm wondering if this is because of the darkness or it's because I'm boring. Okay, good. So next step, a more realistic proof of concept. So the next part of the talk will be, so what I was doing, what I was showing here was a very simple example where I have a simple model for my lens, and I'm trying to fit it with the exact same model. The question is, do my conclusions still apply if I have more realistic lenses and more realistic images? So this is a work that I've been doing in particular in collaboration with Natalie Hoff, who is a postdoc working with me. Most of the results were obtained by her, so all the credit should go to Natalie. Thank you, Natalie. So what do we do to produce these more realistic images? So we take a model that is made of first baryons. So we have a certain baryonic density that we describe with an elliptical static density. We add on the top of that a dark matter halo that will be offset with respect to the baryons, that will have their own ellipticity and that will be described as elliptical NFW. We take a source that we don't take as being a simple static profile, but more of adding perturbations to it. So we have in practice, we used the sum of 5 different static profiles just to make the image a bit complicated. And of course, we are adding these line of sight shears into the game. And now we ask the same question in that context: is there any way that we could infer precisely the line of sight combination with gamma and this guy? So we produced a sample of images. We have 64 in this sample that were produced by drawing randomly all those parameters I talked about. So you can see already by eye that there is a very large diversity in the shape of these images. You have some of them like this one that looks absolutely fantastic, with a beautiful ring with a high resolution. You have some of them like this one that are beautiful rings but with lower resolution because the actual radius in this case is different. And you also have some of them that look absolutely terrible, and that you wonder whether anything can be observed from this. It was to really account for the diversity of the type of images that we would have in a real sample. So let's try to fit them with different models. So the first model we use is what we call the comprehensive model, which is the same one as the one that was used to produce the images. The only difference is that instead of having the 3 shears, we have now only 2. We have the gamma and OS, and we kept also the foreground one, the one that's included in the effective potential. Also, something else is that to be more realistic, we didn't account for the perturbations to the cell-sick profile for the source. So we wanted to account for the fact that we might not have a perfect description of a realistic source that we may have. So this is actually an exact elliptical surfacing that we have in the model that we use to analyze the images. This is how it looks for these 64 images. So what I'm showing on this graph is on the x-axis, the input value of the line of sight shear, the expected one, therefore. On the left part, you have the component number 1, on the right part, component number 2. On the right axis, you have what is recovered, what is the best fit after the MCMC has run, with the error bars corresponding to the ones estimated from the posterior distribution. The dashed line is, well, the y equal x, so what we would expect. So if the recovery were perfect, we would have all the points aligned on it with tiny error bars. It's not the case in the sense that we do recover the trend, and it's really compatible with the input, but we have error bars that can be quite large. To give you an idea, the mean error bar here, if we just take, the mean error we have here is on the order of 1 to 2%. So it's borderline comparable to the signal that we would expect. Also, something a bit weird that we are still not sure to understand is that the recovery of the component number 1 seems quite better than the component number 2. It's a bit, so this is a bit open to debate. We're not sure of why this happens. I have my own little theory, which is due to the fact that we analyze images on square pixels. And so because we have square pixels, you break the degeneracy between what's happening vertically, horizontally, and what's happening transversely. Is the only thing I could come up with. So if you have any idea, this is all very well. So it's still not too bad. The colors, by the way, are representing here as kind of a measure of the quality of the image. So the U quantity that you have here represents the dimensionless impact parameter. So it translates the alignment is the angle between the apparent position of the lens, the apparent position of the source, normalized by the Einstein radius. So if U is very small, so for the darkest colors, it means that you have a very good alignment and therefore a very good Einstein ring. While when the colors are a bit lighter, you have something which is a bit further off and therefore a worse image. And you can see indeed that the very good points tend to have darker colors. We are still on the way to make this a little bit better. We are trying to figure out what could make this inference more efficient. It's work in progress. Just to show now what happens if I'm relaxing some of the assumptions, in the sense that if I'm changing the model with which I'm fitting the images. So let's take what I call the no foreground shear model. So that means that I'm taking the exact same model as before, but I'm removing this guy. So I have a parameter that is not present anymore in the model. The results are not much worse, and actually it doesn't seem so, but statistically they are a little bit better. So these results are actually a little bit better than in the comprehensive model. So that shows that this foreground shear term is completely useless and is completely accommodated by the freedom left by the parameters of the main lens. Now, what happens if instead we decide to use this what I call the aligned model, which consists in assuming that the dark matter and the baryons share the same center. So if we don't account for the offset that there could be between dark matter and baryonic matter in real galaxies, it gets terrible. So that is, it confirms some things that had been seen in the literature, that when you try to fit some strong lensing image with models that are concentric, and that you actually have a galaxy, a lens galaxy, that has some offsets between its various components, you can be completely off when you try to measure the external shear. Another way to say that is that the shear is something that can accommodate for a part of some missing offset. That's a source of worry, because that shows that there are parameters or properties of a lens that could be mimicked by an external shear, and that therefore endanger our capacity of measuring the shear. We also did a test with just an elliptical power law. It's even worse, so we can forget about this. So what can we conclude from this little analysis of the proof of concept? So the first one is that if you have, so you can in principle measure this line of sight shear with realistic images with a precision that is absolute precision in the order of 1%, meaning a relative precision on the order of 100%. So to be made better. And but also that a true poor lens model can easily mess it up completely. So it's something that must be really, so the lens modeling is something that is crucial in this matter. So the next step here would be to test on lenses that would be, instead of coming from exact lens model, that would be extracted from simulations, for example, hydrodynamical cosmological simulations, to see whether the traditional lens models are able to reproduce these things or not. So what? So why are we doing this, and where could this go? So, as I said, my initial goal or motivation is to try to do weak lensing with Einstein rings. So, what we would do, and this is also work in progress, the idea would be the following. On the top of measuring the apparent shape of galaxies and correlating those shapes and correlating them with the number or density of galaxies, we could add on the top of it the information we could get from this line of sight shear wherever we have Einstein rings that could be distorted. The idea would be to add to the standard correlation functions a correlation between the rings, but also correlation between the rings and apparent ellipticity of galaxies, and correlation between rings and galaxy positions. So for people of you who are aware of the jargon of weak lensing, we would go from a 3 times 2 point correlation function to a 6 times 2 point correlation function. The idea is that this would help us beating the effect of intrinsic alignment, for example, because those guys would provide a direct measurement of the shear independent of any intrinsic alignment of their sources or of their lenses. So that would be one of the ultimate goals. And as I said to Łukasz, at the beginning of this talk, this will be feasible with the survey like Euclid, but also with the Rubin Observatory, LSST, because these are expected to observe about 10 to the 5 lenses in the future. And this brings me to my conclusions, and I think I've been quite quick. It's good. Let's leave this time for questions. So the weak lensing of strong lensing features not only 1, but 3 external shears that we could try to measure. Actually, not all 3 of them are measurable. It's only a special combination of them, which is this thing that we call the line of sight shear. We made a proof of concept that showed that the line of sight shear can be extracted in principle with not a great precision, but at least it's possible from images if the lens model is sufficiently rich. And by combining the weak lensing of Einstein rings with normal cosmic shear, we could greatly, we hope, improve the performance of the Euclid survey. This, I thank you for your attention.
Thank you very much.
Light on again.
Yeah, well, we can still see you, and you
Good.
can see action. Thank you, Pierre. Questions here from the audience?
So I have a question. Do you want to start because
Go for it.
So referring to Łukasz's question, I presume complete rings are perfect, but we'll see non-reducible functions, or we will see even more bananas. How good are they?
I think so. It's still something we have to investigate. But so you don't need an absolute ring to have that, because the idea is that in these images you have information in every pixel that you see. All that contains information and could have and is affected by this shear. So you don't need absolutely a perfect ring. The idea is that more pixels are covered, the better it is. But we still have to look at how our results, the precision of our results, correlate with, with, for example, the signal to noise. I mean, we tried, the best thing we could come up with again was this U parameter, which exactly translates the alignment between the lens and the source. So we do see that, yes, for the darker one, the best rings that we do have tiny error bars here. But you see that you have also some ones, like this one has a U value which is probably around 0.3, meaning that you don't have here a perfect ring. You know that you would have like a big banana instead.
And how are, for example, crosses any good or?
Good question. So an Einstein cross. So if you have an AGN at the center of the source galaxy that's yielding like a big, beautiful four-imaged, multiply imaged quasars, it's not enough to break the degeneracies, because now you have really like 4 points, and these 4 points could have that same position for very different configuration of the main lens and of the shear. So having only those 4 images is not enough. You really need something covering around the lens to have it.
Thank you.
Any more questions? So you actually had a slide asking, so what?
Mm-hmm.
So what?
So what? No. So that's the thing. This is a pretty recent attempt, in the sense that for a while this external shear in strong lensing modeling, it's something that people have been putting in the lens model forever, just because they noticed that it was making the fits better, and it was considered nuisance parameter. So here we're trying really to reverse the logic and to consider it as a signal that you could try to measure. What I'm taking out of this analysis is that it's still possible. I'm optimistic about the fact that we could measure it, because the degeneracy between, for example, the ellipticity of the main lens and the shear is actually quite weak. You can really distinguish between these two things. However, we're still far from having tested everything. And that's why I think the next step is really to confirm that on lenses extracted from simulations, for example. This is really something we have to do first. The second branch of this project is now taking those numbers as is, and given the number, the sky coverage of Euclid and the number of lenses that we expect, if we actually do these correlation functions, seeing what is the gain in the measurements of sigma 8, for example, what is the gain in the breaking the degeneracy with intrinsic alignment parameters, and this is something that we still haven't done. We're working on it. So I can't answer this question yet. I hope that in like maybe a year, I can say that yes, so this precision on the shear, on the line of sight shear, will give us that gain on measurements of sigma 8 omega m. Also, there will be the step of applying it to real data. We'll start with JWST because there will be very beautiful images, but maybe eventually Euclid. Problem with Euclid will be the numbers, how to make those fits for tens of thousands of images. This will be a challenge. I guess machine learning will be the solution, unfortunately.
Unfortunately.
So someone told me once, I think it was Simon Wheeler, he said, as a theorist, you have to be against machine learning. Or you have to be, you're not against, you have to be careful. Like the idea is that my approach with machine learning is that I will use it only when it's for what it's made of.
Yes, I agree.
I'm a bit scared of it, and I want it to steal my job.
It's mostly the tool for experimentalists.
It's impossible to change his job. I haven't.
Sorry.
So what's the Euclid launch date?
The what, sorry?
Euclid launch date.
Yeah, it should be next summer, to summer 2023. That's the what's expected now. Yeah, it will be, the contract is not signed yet, but it should be with SpaceX. Because of,
For Euclid. Anyway, so thank you very much. Thank you for the questions. Thank you, Pierre. And let's thank our speaker again. Thank you. And as I said, we will be going for dinner later tonight. So feel free to join us. Thank you.